Hello viewers, in today's session we are going to discuss a very important concept from logarithms of complex quantities, right? So in this session we'll see the concept of principal value and the general value of logarithms of complex quantities, right? And moreover we'll also see the concept of logarithm of a real positive quantity, and then we'll see the logarithm of a real negative quantity, and then we'll see the logarithm of a purely imaginary quantity, right? So let us see all these concepts. And here in order to discuss the concept of logarithms of complex quantities, let us start with the function, say f of z, that is equal to e raised to z, right? So we'll start with this function which is exponential function, and here z is a complex number, right? So let us consider f of z is equal to e raised to z, that is equal to w, where z and w both are complex numbers. So let us take z is equal to x plus iota y, and w as u plus iota v, right? And I square is equal to minus 1. So now we know that this exponential function e raised to z, where z is a complex number of the form x plus iota y, is periodic in nature, right? And we have already proved this, the periodicity of e raised to z in one of our videos. And here the period of e raised to z is given by 2n pi I, where n is 0 or a positive or a negative integer. So e raised to z is a periodic function with period 2n pi I, right? So now let us consider the expression e raised to z is equal to w. Now the period of e raised to z is 2n pi I, so we can also write w as e raised to z plus 2n pi I, due to this definition of periodic function. That is, if we have a function, say f of x, and if the period of f of x is t, then f of x plus t can be written as f of x, right? So here now let us take the natural log of both sides. So we have here a log of w to the base e. Here we have log of e raised to z plus 2n pi I. So here using the properties of logarithms, we can now write z plus 2n pi I, and here we have log of e to the base e, and log e to the base e is 1. And here we have used this property, that is log of a raised to b is given by b times logarithm of a to the base e. So here we have 1, so we have z plus 2n pi I. So now we can write the logarithm of w to the base e is equal to z plus 2n pi I. So this is an important expression. So now from this expression, we can conclude that the logarithm of a complex quantity, that is w, which is of the form u plus iota v. So the logarithms of a complex quantity has an infinite number of values, because it depends on n, right? So as we vary the value of n, we can get different values of logarithm of the complex number w. So the logarithm of a complex quantity has an infinite number of values, and so this function is a many valued function, right? And the principal value of logarithm of w can be obtained by taking n is equal to 0. So when we take n is equal to 0 in this expression, then the principal value of logarithm of w is given by log w. Here we have the base e, and this is equal to z, right? So from this expression we conclude that the logarithm of a complex quantity has an infinite number of values because it depends on n. As we change the value of n, we get different values of logarithm of w, and the logarithm of w, which is a complex quantity, has the complex quantities, that is logarithm of a complex quantity is another complex quantity, because here we have 2n pi I, and the logarithm of a complex quantity is a many valued function, and the principal value of logarithm of a complex quantity can be obtained by taking n is equal to 0, right? And here the general value of the logarithm of a complex quantity is denoted by the capital L, that is we'll write a log of w. So when we use this notation, then it implies that we are taking the general value of the logarithm of w, right? And when we use the small l, then it implies that we are considering the principal value of the logarithm of w, right? So now the general value of the logarithm of this complex quantity w can be written as capital L. Here we write the capital L, and here we have log w, and here we have e, and for z we can now write here log of w, and here the base is e, and here we have 2n pi I. So this is an important expression. So here the capital L denotes the general value of the logarithm of the complex quantity w, and the small l denotes the principal value of the logarithm of this complex quantity w, right? So once we put here n is equal to 0, that is taking n is equal to 0, then we obtain the principal value of the logarithm of w, right? So now consider the complex number z, that is equal to x plus iota y, and let us now write this complex number in polar form. And we know that z is equal to x plus iy can be written as r times cosine theta plus iota sine theta, and using Euler's formula we can also write it as r times e raised to I theta, right? So this complex number z, which is equal to x plus iy, where x is the real part and y is the imaginary part. So now comparing the real and imaginary parts on both sides, that is x plus iota y is equal to r cos theta. Then we have here I r sine theta. So we have x is equal to r cos theta, and here we have y is equal to r sine theta. So squaring and adding, we have x square plus y square is equal to r square cos square theta plus r square sine square theta, that is r square cos square theta plus sine square theta. So cos square theta plus sine square theta is 1. So we have r square. So here we have x square plus y square is equal to r square, and if we divide y by x, Then we have y over x is equal to r sine theta divided by r cos theta, that is equal to tan theta, because r and r get cancelled and sine theta over cosine theta is tan theta. So we have a tangent theta is equal to y over x, right? Okay, so now we have x is equal to x plus iota y. So let us take the general value of the logarithm of this complex number, that is z. So now using this result and replacing w by z, the general value of the logarithm of the complex number z can be written as a log z to the base e, and here we have 2n pi I, right? So the general value of the logarithm of this complex number z can be written like this, and it depends on n, right? So when we take n is equal to 0, then we get the principal value of the logarithm of this complex number z. So now we can write log of x plus iy is equal to log of x plus iy, and here we have 2n pi I, and remember here we have the capital L denoting the general value of the logarithm of this complex number, and this L, that is the small l, represents the principal value of this complex number, right? So now we can replace x plus iy by r e raised to I theta. So here we have r e raised to I theta, here we have 2n pi I. Now using the laws of logarithms, here we can now write log of r plus a log of e raised to iota theta, and here we have 2n pi I. So now we have log of r is given by square root of x square plus y square, that is x square plus y square raised to half. So here we have x square plus y square raised to half, and here using the laws of logarithms, we have I theta, and then a log of e to the base e plus 2n pi I, right? So now we can write a log of x square plus y square, and taking this half to in front of log, and here we have I theta. A log of e to the base e is 1, so we have I theta, and theta can be given from this expression. So theta is a tan inverse y over x. So here we write tan inverse y over x, and log of e to the base e is 1, and here we have a 2n pi I. So therefore, here the general value of the logarithm of the complex number x plus iota y is given by this expression, right? And remember here this capital L denotes the general value of the logarithm of x plus iota y, and this small l, it represents the principal value, right? So here this small l represents the principal value, and here we can see that the general value of the logarithm of a complex quantity, it depends on n, right? And as we vary the value of n, we get different values of the logarithm of a complex quantity. So this is a many valued function. So now if we take n is equal to 0 in this expression, then we get the principal value of the logarithm of this complex number. And the principal value of the logarithm of z or x plus iota y is denoted by small l. So here we have log of x plus iota y to the base e, that is equal to, here we write half, then we have log, and here we have x square plus y square plus iota times tan inverse y over x, and here this term is 0 because we are considering n is equal to 0. So this expression gives us the general value of the logarithm of x plus iota y, and here this expression gives us the principal value of the logarithm of this complex number x plus iota y. So in the general value of the logarithm of x plus iota y, we have 2n pi I, which is an imaginary number, and here in the principal value of the logarithm of x plus iota y, we have n is equal to 0. So we do not have this term, right? So now this expression can also be written as half, and here we have log to the base e x square plus y square, and here we can take I common, so we have I, and then we can write 2n pi plus tan inverse y over x. So this expression can also be written like this. So now consider three cases. So here the first one is logarithm of a real quantity. The second one is logarithm of a real negative quantity, and the third one is logarithm of a wholly or purely imaginary quantity, right? So let us first consider the case one. So here we'll again make use of this result to discuss these three cases. So now when we have to consider the logarithm of a real quantity, then we have to take y is equal to 0, because z is x plus iy. So when we take y is equal to 0, then we have x plus I times 0, that is simply x, right? So let us find out the logarithm of a real quantity. Here the imaginary part is 0. So using this result, we have the general value of the logarithm of z, and now in this case z is equal to x, and here we have a log of simply x, because I is y is 0, and here we have 2n pi I, right? So this expression suggests that the general value of the logarithm of this real quantity x is given by the principal value, that is log of x to the base e plus 2n pi I, where n is 0 or some positive or negative integer. So this shows that a real positive number, that is x, has only one real logarithm corresponding to n is equal to 0. So if we take n is equal to 0, then this expression reduces to a log x to the base e is equal to log of x to the base e. So this proves that a real positive number has only one real logarithm corresponding to n is equal to 0, and an infinite number of imaginary logarithms corresponding to other values of n, right? So when we have n is equal to 0, then the logarithm of a real quantity is a real number. So now consider the second case, logarithm of a real negative quantity, right? So here we'll take y is equal to 0 and x is equal to minus a, where a is some real number, right? So here z is equal to x plus iota y. So taking y is equal to 0 and x is equal to minus a, we have minus a plus I times 0, that is equal to minus a. So now using this expression, the general value of the logarithm of z. So now in this case we have z is equal to minus a. So here we have minus a, then we have log e, and here we have x plus iota y. Y is 0 and x is minus a. So we have minus a, and here we have 2 and pi I, right? So now further we can simplify this expression, because here minus a can be written as a times minus 1, and in polar form, if we express this number in the polar form, then minus 1 can be replaced by e raised to iota pi, right? So here we have a times cos pi plus iota sine pi. So we have a cosine pi is minus 1 and sine pi is 0. So we have simply this is 0. So we have minus a. So minus a can be replaced by a times e raised to iota pi. So here we write log e, the base e, and here we have a e raised to I pi, and 2n pi I. So now let us simplify it. So we have a log of a plus log of e raised to iota pi plus 2n pi I. So now we can write the general value of the logarithm of this real negative quantity, that is minus a, as log of a plus here we have simply I pi, because a log of e to the base e is 1. So here we have 2n pi I. So now we can write the general value of the logarithm of minus a as a log of a plus, here we can take I pi common. So we have 1 plus 2n, and here we have pi I, right? And remember, n is 0 or positive or negative integer. So here we have this important expression. Now this expression suggests that a real negative number, that is minus a, has an infinite number of imaginary logarithms, because here the logarithm of minus a, it depends on n, right? So when we take n is equal to 0, then 1 plus 2n is equal to 1, and the logarithm of negative a is still an imaginary quantity, right? Because see, when we take n is equal to 0, that is n is equal to 0, then the general value of the logarithm of minus a is given by log of a plus pi I, and it is still an imaginary quantity, right? So that's why the logarithms of negative real numbers, that is negative real quantities, are not defined in the set of real numbers. Now, for example, if we take a is equal to say 1, right? Then we have a log of minus 1 is equal to log of here 1, and here we have 1 plus 2n, and here we have pi I. Now this is equal to 0. So we have 0 plus 1 plus 2n, and here we have pi I, that is 1 plus 2n pi I. So the logarithm of a negative real number, that is a real negative quantity, is not defined in the set of real numbers, because this quantity is an imaginary quantity or a complex number. Because if we take n is equal to 0, then we have here pi I, and this suggests that the logarithm of a real negative quantity or number has an infinite number of imaginary logarithms. So now consider the third case, that is logarithm of a wholly or purely imaginary quantity. So in this case, we'll take x is equal to 0. So when we take x is equal to 0, then the value of z, it becomes 0 plus iota y. So here we have iy, and iy is purely imaginary quantity. So let us substitute the value of z as iota y in this expression. So we have the general value of the logarithm of z, that is iota y. So here we have the purely or wholly imaginary quantity, that is iota y, and here we have log of x plus iota y. So x is 0, so here we have iota y, and here we have 2 and pi I. So now let us simplify this expression. So here from the polar form, we can now write I is equal to e raised to I times pi by 2, right? Because from Euler's formula, we can write e raised to I pi by 2 as cos pi by 2 plus I times sine pi by 2. So cos pi by 2 is 0. Here we have sine pi by 2 is 1. So we have simply I. So now we can replace this I by e raised to iota pi by 2. So now we have log, and here we have y times I is e raised to I pi by 2. So here we have 2 and pi I. So simplifying this expression by using the laws of logarithms. So here we can use the product rule. So we have log of y plus a log of e raised to I pi by 2, and here we have 2 and pi I. So this is a log y, and here we have I pi by 2, taking I pi by 2 in front of the log notation, and log e to the base e is 1, and here we have 2 and pi I, right? So we can now write log y, and here taking pi I common, so we have 1 plus 2, here we have half, and then we have 2n, and here we have pi I, right? So the general value of the logarithm of this purely imaginary quantity iota y can be written as log, that is the log of y plus, and here we have 2n plus half, and here we have pi I, right? So now this expression suggests that the logarithm of a purely imaginary quantity iota y, it comprises of two parts. That is, this is the first part, this is the second part. So the first part is a real number, that is a logarithm of y to the base e, because when we take z is equal to x plus iota y, then x and y both are real numbers, right? And here this is the second part, is a complex number or an imaginary number, right? So the general value of the logarithm of a purely imaginary quantity can be expressed by this expression, and from here we can see that the general value of the logarithm of iota y is a a many valued function, right? Because here if we vary the value of n, then we can get an infinite number of logarithms.